the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 40, where today we're going to be talking about the big math, i.e. calculus. So today we're basically just going to be kind of getting into, calculus in general, why it's so important, how it helps us. But also a quick note before we start. In the last episode, I mentioned that was episode 40. It wasn't. It was actually episode number 39. Some of you might have caught that. So this is actually episode number 40. So 10 more for the big 50. So yes, any news we want to get out before we start the big math?
2,500 followers on
true.
Spotify. That's awesome.
True.
I don't really think there's anything else. One more thing, if you are watching on or listening on Spotify or Apple Music or anything else, we are now on iHeartRadio.
Oh.
And
Nice.
Amazon. I don't know, something like
Amazon
that.
has a podcast, like Amazon
yeah.
Podcast or something.
Yeah,
Oh,
I think
really?
we are pretty much everywhere now.
I think we always were on there, right? I don't.
Probably.
Not sure.
Anyways, this episode is also being recorded on YouTube.
Or
where
on
we
Zoom.
are recording on Zoom.
Mm-hmm.
So you can see our faces if you want to
Yep.
go and do that.
Yep.
Other than that, we can just get started and talk about calculus. So we do understand that some people that listen to our podcast have not done calculus yet.
Exactly.
There are a lot of high school students out there that do listen to the Math and Physics podcast. And so the first thing we are going to talk about is, what is calculus?
Mm-hmm.
Because before I took high school calculus, I had no idea what calculus was. If someone would have said, limits and derivatives, I'd been like, I don't know, man. I've just been adding numbers and drawing graphs my whole life. So
Yeah, because also in grade 11, if I'm not mistaken, we don't do like any traces of calc, right? Like no limits, nothing, right? Exactly.
No.
Yeah. So grade 11 kind of doesn't really prepare you for grade 12 calc at all. I think it's a kind of a whole new regime itself. But I think it's kind of interesting the way they do it. Like, did you guys have like advanced functions and then transitioned into calculus, like something like that? Yeah, you had something like that too, right? Mm-hmm.
Yeah, that's right. We just did like advanced functions, drawing graphs, doing sine and cosine, inverse functions. And then after that, you go straight into calculus, which is just limits, derivatives, critical points, drawing graphs. And I think that's it. After that, we do a little bit of vectors.
Oh, yeah. You guys did vectors too? Even though our course was called Calculus and Vectors, we did like 1 week, if not 2 of vectors. Like that's
Really?
it.
I think I had 2 units.
No,
I think
really?
I had 2 whole units. Yeah, we did.
Wow, I didn't know that. That's pretty crazy.
We did like 1 unit on just vectors and dot products and cross products.
Yeah,
and
we
then
didn't
the
even
next
do
unit.
Cross-product. No, we did.
Yeah.
No, we did cross product. Well, we just did it in 2 weeks. Like, no joke. It was crazy.
I don't know.
It's just like, okay.
The last unit was like planes and intersections of planes and lines and things like that.
That really gears you up for linear algebra.
Yeah, it does.
Very much.
That's why like first semester of linear algebra in university was very
first
easy.
half of the first semester, because it's only one
Oh
semester.
yeah, true.
Of course.
First half.
Yeah.
That's right.
Also, to be honest, like drawing graphs in calculus is very underrated in my opinion. Like I think it is so useful to draw graphs, and I mean obviously we're gonna come to why it's so important and stuff like that.
Absolutely.
But I think just
and
I hated it.
remember
No, that's why I wanted to say it, because I actually hated it in grade 12. Just because I'm like, what is the point of drawing so many graphs? Like, we're trying to do math here. I just didn't really understand it until I really came to university math. And, if you can't visualize it, like, it's really hard to, do the problem. Like, sometimes visualizing it just really helps. And that can obviously be done with graphs, right? So,
yeah, and
important.
I remember my math teacher, while I was taking advanced functions, he was like, don't worry about like where the local mins and maxes are. Like all you have to draw is like the general shape.
Yeah.
And he's like, yeah, next semester you'll be able to draw it like precisely. I'm like, wait, how? How do you find the local
no
max? All you know is like where it crosses the whatever it's
The
called.
x-axis.
Yeah.
Right, yeah.
Well, no, there's another name. Isn't it the abscisses or I don't know. Whatever.
Oh, like asymptote?
No, like in French, it's abscisse. It's where it crosses it's like there's like a name for a point that crosses the x-axis.
Oh, okay. I mean, it's just...
Anyways.
Yeah, I mean, yeah. It's just called roots in English, I think. It's just
Okay,
called
sure.
just roots. You know, like roots
Sure.
of the graph, yeah.
Sure. But yeah. So first of all, what is exactly calculus? If I had to say it, give a description for calculus in just a few words, it would be rate of change.
Yeah,
That's it.
for sure, for sure.
There are more things that you learn after you learn about like limits and derivatives, but everything in calculus is pretty much a limit. I think what have we
Yeah.
done that is not a limit?
If you think about it, it can all be represented in terms of limits. Yeah, and I think
Yeah.
rate of change is like the perfect phrase to describe calculus if you're just saying it like just describe it in one phrase. Because at the end of the day, like all of calculus just depends on how one variable is changing with respect to another. That's basically the entire idea of calculus, right? Like when it comes to
Basically.
derivatives, it's one variable divided by another. When it comes to integrals, it's multiplied and stuff like that. So it's all about just how they're changing, and that's the whole deal. That's the whole deal. So at the end of the
Right.
day, I think the roots, the foundation is pretty basic, even though it can definitely get very complicated.
Yeah, that's right. And the first thing that any calculus course starts off with is limits.
Yeah.
And to be honest, I didn't understand the importance of limits until I got to university.
True.
I did
Very
I
true.
did an entire unit on limits in high school, and then we went on to derivatives, and I'm like, okay, well, there's like the product rule, the sum rule, and all that stuff. Why do I need limits anymore? I just kind of threw them
Exactly.
aside and then went on
Exactly.
to doing other things in calculus and didn't really think about why limits are so important until we got to university, which you kind of dive a little bit deeper into what limits actually are instead of just thinking very like hand wavy around the topic. Like in high school, when they describe what a limit is, they're like, well, when you get very close to a value, what happens to your function when it's very close?
That's the whole idea.
That's
the whole
basically all they tell you, right? But they don't actually tell you like formally what a limit is and how to write down like it's not just kind of this definition where they say it to you, but there's a lot of holes that you
Also,
can
yeah.
find.
I kind of believe that we have, I think, a better understanding of limits definitely because of the fact that we did a proof-related math course, though. I don't think, like, general university math, like, for example, the U of T version of that is, like, 135, right, and 235, like, those are the course codes. But, like, general university math for, like, non-science specialists, I guess, like, I'm not sure they even touch up on, this formal definition of the limit. And that's why I think, a lot of people, even in university, are like, I don't really see the points of limits when, as Parker said, all these derivative rules are right here. Like derivative rules, like these tricks that we use to kind of solve these derivatives are it's kind of bad in some way, in the sense that we don't really understand what's going on. We're just using these rules without really understanding why they work, and
Exactly.
I think that's a really important part of it.
And Ray and I were thrown in unknowingly into this proof class.
That was
to
crazy.
be honest, I was expecting just a regular like computational,
Very much so. I was not
calculus
expecting
class.
that. Yeah.
As soon as we got thrown into doing logic and proofs and proving limits and all that, I was like, man, what is going on?
I remember in high school too, for any, like, especially a mathematical proof or in physics, for example, like if there was any kind of proof relating any equation, we were always told that you don't really need to worry about the proof. You mainly need to just worry about the result of the proof, or the theorem behind the proof. And we're just like, okay, let's just take it. But the thing is, you never really understand it. You never really understand why that theorem works unless and until you prove it. And I think that's why this proof, and also like why we're going to be talking a little more about how you can, like, the limit proofs and stuff. I think that really helps into understanding why these limits are so important.
And at the end of the day, I'm happy we did do a proof related class, because you really do get to see the machinery behind what you're actually doing, and why the product rule is a thing and why the quotient rule is a thing. So let's talk about why do we need calculus, right? So calculus is a big one, because it really provides results for things that you just can't do without analyzing limits. And without looking at very small quantities and very large quantities. And I'm talking about, as you're looking at the result of a function or a change in the function as your value gets very, very small, and then, infinitesimally small or infinitely large. So, for example, how about this? You drop a ball from, 1 meter, let's say, and you can ask yourself, okay, what is the average velocity of that ball? Well, you can just calculate the time it takes for the ball to hit the ground and, divide 1 meter by that time, and you'll get the average velocity. But you know that when you let go of that ball, it's not moving, right? You need some interval of time to pass before it starts, gradually accelerating. And by the time it hits the ground, it's going very, very quickly. Well, here's the question that calculus kind of asks in an indirect way. It's, okay, well, what about halfway through? Halfway through the descent, how fast is it moving exactly at that point halfway through? And you can ask yourself, well, you can calculate the average velocity of, it moving half a meter, and then the average velocity of the second part of that descent. And then if you just keep cutting that distance down to get closer and closer to just a single point, and then you might ask, well, you can't really calculate the average velocity over a single point, because then you're dividing by 0. And so that's when limits come into play, where you ask, well, I can take the limit as that distance goes to 0, but I still get a result, right? It's kind of weird when you've never done calculus before, but that is something that happens. You take the limit as the distance goes to 0, and you still get a finite velocity. So it's like you're dividing by 0, but you're not, because the time it takes also decreases.
Exactly.
And so then you're just doing like you're doing like a rise over run with very small values, but that ratio is what you're looking for, right?
But again, that is kind of a description also of how like we can describe derivatives, right, with the use of limits. So what you just described there was more of a derivative, right? I mean, the idea of a limit obviously considerably helps the idea of the derivative, because it, the formal definition, quote unquote, of the derivative is a limit definition at the end of the day, right? But basically, like as Parker was saying, even though the values, as he said, is divided by 0, because the average, you're only taking it over one number. So how can you do that? Again, the limit is simply giving you an idea of what the value is approaching. And I think that is a very important concept that was kind of driven hard in first year of math, where the limit as something is approaching something is not simply as x equals this value, or as, what is happening. The idea of a limit is simply what is happening around that value. And as you're moving closer and closer to that value, what is your function doing? And I think that's the whole idea of a limit. And when it comes to derivatives, it's simply about taking that rate of change, right? And when that rate of change, equals it's divided by 0, then what do? That's exactly where limit comes into play, right? So limits have a lot of roles in calculus, and it's kind of also where a lot of it was defined from.
And for to describe a limit formally, there's something called an epsilon delta proof, which we are absolutely not going to describe right now.
I mean, we can give a general idea, though. I think we can give a general idea.
Yeah, we can give a general idea, but there's no way that we're going to convey the full picture of what's actually going down.
The very, very general idea of an epsilon delta proof, is basically let's say you have a function like y equals x squared, right? Or any kind of function like that. Just not getting into the math, just the theory, just the idea behind an epsilon delta is basically, let's say you want to find your value of your function, let's say at x equals 5. Right now, obviously, you already know what it is. It's 25 because it's x squared. But let's say you don't know the value. So the entire point of the epsilon delta is if, let's say, you have x equals 5, the idea of, once again, this limit definition is as you get closer and closer to x equals 5, your function gets closer and closer to y equals 25. And that's basically the epsilon delta. So let's say you take one interval away. So your x equals 6 and x equals 4, right? Then what does your function equal? Your function would be 16 and 36. And as you get closer and closer to x equals 5, the idea is simply your function value is getting closer and closer to 25. So what that proves, what the epsilon delta can help you prove is, let's say you're trying to prove why the limit as x approaches 5 of x squared equals 25. Let's say you're trying to prove that. Now, if you're trying to prove that, that is where you would use this epsilon delta. That I can find some value close enough to x such that all values of your y are very close to 25. Right?
And basically, another idea that ties into that is that calculus is all about zooming in.
Yeah.
Right?
Yeah.
The idea of zooming in infinitely kind of also ties into continuity, but what I was trying to say is that you have a point, and usually when you're taking or trying to prove a limit, it's going to be some kind of function that has a discontinuity at a point.
Yeah.
And usually when you would draw that on a graph, you would draw a hole, right? But what you need to understand is that hole is just one point, which means that you can zoom in as close as you want to that hole, and there will always be values to the right and to the left. And so to prove that the limit exists, or the value, what am I trying to say here?
The limit
the function
equals a number,
converges to that one point.
Discontinuous,
right?
Yeah.
What you're actually trying to do is you're basically zooming in very close, and you're saying, well, the closer and closer you zoom in, the closer and closer the values actually reach that point. But you have to be careful, because when you're taking a limit, it doesn't, the function doesn't actually have to be defined at that point.
It's true.
It just has to be defined very, very infinitely close to that point. And that's kind of the most fundamental idea in calculus, I believe.
Another important thing in why do we need calculus, where does it come, in real life? Because, I think at the end of the day, a lot of people in high school, especially that are dealing with calculus, are like, when am I ever going to use this in real life? This is so pointless, right? You're like, this is just a bunch of math. This is so, ridiculous. But I think we were watching a video that was kind of like a prerequisite for one of our lectures in math. And I think this example, I don't know why, it just really drove the point home So let me just give you the example, right? Let's say you're running a business and you have a bunch of variables, right? You have the amount, let's say, that you are profiting, let's say your revenue in this case, the amount you have to pay your workers, the amount you have to pay, let's say, I don't know, that your partners, you have a bunch of variables with different values. And your net profit the net profit on your business will equal some function of those variables, right? Like, let's say it's simply, simplest example. You have revenue and you have cost, right? Let's say you have a revenue and you have a cost. That's it. You have two variables. Your goal is to find your profit. Well, it'll simply be revenue minus cost, right? I mean, it's pretty standard. So that is your profit function. Now, the goal in calculus and where it really becomes important is, let's say, now, obviously, as a business owner, you want to maximize your profit. You want to get the best possible results. Obviously, you want to maximize your revenue and minimize your cost. That's your end goal, right? So you have some function of these variables, of, in this case, just revenue and cost. But obviously, in a real business, it's going to be a lot more variables than that. So you have some function of these many, many, many variables, and you want to calculate the, what we call in math, quote unquote, global maximum of this function. So once again, this is where calculus comes into play, right? Like finding these derivatives, finding these limits at certain values. So certain values of the function will have certain characteristics. Now, I don't think we want to go too deep into the math behind it, but just like generally speaking, certain points on the function, like certain xy points, will have certain derivatives. And when you check them together, okay, this is not really explaining very well without the math. It's a little hard to do it without the math itself. But basically, the idea is you can find this global maximum of your function, of this many, many, many variables with calculus. And that's what calculus can do. So it can maximize your profit in a business. And I think like that example just really made sense to me. Like how, because I mean, it's very realistic, for a profit function to be multiple variables and obviously just spits out one number. So if you're trying to find the maximum of that number that it spits out, what do? You have to use calculus. And I think that's also a really big part which calculus plays in real world, right?
Mm-hmm. And I wanted to mention, I think it would have been pretty useful to mention before you talked about all this, but derivatives tell you the rate of change at a point. So if we're just talking about one-dimensional calculus here, you pick a point on your graph, you take the derivative of the function, and you plug in that point that you want, and it'll spit out the rate of change. So if you have a really high rate of change, if you move a little bit to the right, you're going to be increasing your function by a lot. If your derivative is 0 at that point, that means if you move a tiny bit to the right or a tiny bit to the left, then your function is not going to well, it is going to change, but it's like very locally, the value is going to stay pretty much the same. Mm-hmm. And so, we call those critical points. And those are like the points, if you know y equals x squared, right? There's a point where there's the summit, right? The bottom. Mm-hmm. At that point, at the bottom, that's where your rate of change is 0, because it's, if you draw kind of the tangent line to it, it's going to have a slope of 0. And we call those critical points because those are the minimums, or the local minimums, the local maximums, and also possibly global, but there are tests that you have to do to find those. But those really tell you kind of they tell you the right information that you want to know. Because if you have like just a one-dimensional profit function, right? So your profit is solely based on one variable, let's say. And so you want to see, where is your profit going to be the maximum when, at what number you evaluate your variable at. Does that make sense?
Yeah. I mean, like the maximum possible value of all of your variables.
So what you're going to want to look for is obviously the global maximum. And that global maximum is going to be at a point. And let's say, you're not looking at boundary conditions, because this will just complicate the whole thing.
Oh, you're getting it. Okay, yeah, that's true.
This is just going to complicate the whole explanation here. But your global maximum is going to occur, if it occurs at all, it's going to happen at a point where even if you move to the right or the left, you're not going to go any higher. You're already at that point. So your derivative is going to be 0. So that's how you solve for those important points. You find points where the derivative is 0, and then you check.
Exactly.
Is it a high point? Is it a low point? Is it a local min, local max?
And those important points are what I was basically trying to talk about in the global max of that profit function example, right? Like once you find those critical points, those critical values, you can just plug them in and find out which one's the highest, and boom, that's your global maximum, right?
Yeah, and those critical points translate directly into like multivariable calculus. Of course, some examples of visualizing these critical points can be very difficult if you're talking about a 27-dimensional input space and all that stuff.
Yeah.
So it's not always easy to imagine, but the easiest one would be like if you have a surface, right? So you have two variables. Your input lies somewhere on a surface, and your output is just it's a scalar valued function. So every input has just a single value as your output. So you
basically think of like kind of like a 3D like a 3D graph where like your XY plane is just flat and this Z axis now is just pointing straight up. So any value on this flat, plane will just point to a certain Z value. Yeah.
And so you can check points that have, we call it gradient. This is gonna get complicated too quickly.
Yeah, a little bit.
Okay, let's not talk about gradient.
Let's not talk a little bit about
gradient.
Yeah, I think that's another discussion for another day. But because remember, this one is the high school demographic calculus. So let's just stick to that.
Yeah,
but
actually, let's not talk about multivariable calculus.
Yeah, let's not. So just continuing with derivatives, I think a really important idea with derivatives is higher order derivatives, and I believe this is taught in high school, right? Yes, for sure. Yeah. So higher order derivatives, and I think the best example for this is think of the exact same thing that Parker was saying with a ball that you drop from 1 meter high. Right? Now, if you want to find the average velocity, as he said, you simply take your distance and you divide it by your time. But now, remember, when you drop your ball, right, 0 speed, somehow it has X amount of speed when it hits the ground. So it obviously accelerated. So now, if you want to calculate the acceleration of this ball, then what do you do? So the acceleration is basically a rate of change of the rate of change. Let me explain.
So remember the golden word, right? The golden word of calculus is rate of change.
Exactly.
So if you take a derivative, you find the rate of change at a point. If you take a second derivative, you're finding the rate of change of the rate of change, which, if your speed is increasing, then you're accelerating. If your speed is decreasing, then you're decelerating. But if you're going backwards, and then you're going backwards faster and faster, then you're technically decelerating because you're going more and more negative.
More backwards. Exactly. Yeah, so I mean, that's where the second derivative, the third, like all these higher order derivatives come into play, right? Where higher order, like for example, as we were just saying, like acceleration, kind of the rate of change of the rate of change, right? Where velocity itself is meters per second, acceleration is meters per square second. So what you're basically doing is you're simply taking the rate of change. Yeah, meters
per second squared.
Second squared, so square seconds. That's what it's square seconds.
Okay, sure.
You know how you say square centimeters? It's the same thing. Square seconds. Kind of thing. Okay. Anyways, so even higher order derivatives, like I think it's the 4th, 5th, and 6th derivatives of position with respect to time, is known as snap, crackle, and pop. You guys might have heard of that. I don't know. I just really wanted to mention that. Have you never heard of snap, crackle, pop? Okay, so if anyone's a Rick and Morty fan out there, definitely send us an email because I would love to meet some Rick and Morty fans. But yeah, so snap, crackle, pop is just like, they say it sometimes. And it's basically the 4th, I believe it's the 4th, 5th, and 6th derivatives of position with respect to time. So it's basically like if you differentiate acceleration, you get something called jerk. So like how fast your acceleration is changing is called jerk, right? And it kind of makes sense because it's kind of like let's say you're jerking in a vehicle, right? You're basically like jerking back and forth.
That did not come out right, man.
I mean, okay, that sounded so wrong. That's not what I meant, and you know it. I meant like back and forth, man. Like you understand that. Obviously, for the non-viewer participants, you might have not seen that thing that I was doing, so it might have not made sense.
You said we're jerking in a car back and forth, man.
Okay, I apologize for those choice of words, but I think people understand what I'm trying to say. Like the change in acceleration over time is the jerk. I mean, that's just what it's called. And then when you differentiate the jerk, you get snap, crackle, pop. Wait, right? Because acceleration is 2, 3. Yeah, then you get snap, crackle, pop, I believe. So, I mean, not that it's anything important. It's just.
But do you know what those things are?
I mean, as I said, it's just the 4th, 5th, and 6th derivatives with respect.
Yeah, but what do they
time.
Represent?
That's all they. I mean, they're just cool words, I believe. I don't think they represent anything. I mean, okay, I could be wrong. It's just that I heard of this because of Rick and Morty, and I searched it up, and I'm like, oh, that's cool. So
yeah,
I just thought I should share it.
Obviously, it's going to be the rate of change of the rate of change of the rate of change. But like, what does that mean physically if you're talking about velocity and
again, I think it's a little hard to explain that way because I think like up to jerk is really where all you can really kind of visually explain and understand. But I think beyond that, like rate of jerk. Oh my, this sounds so wrong, bro. It's so weird. But you know what I mean? Like the rate of jerk with respect to time. Like what even is that? Like,
okay, let's just move on here.
Let's just move on. So those were higher order derivatives. Quite important.
So after derivatives,
comes
you
the big
see
one.
Something called an antiderivative.
Oh.
And turns out that, taking derivatives is very, very easy compared to taking reverse derivatives.
So the antiderivatives, also called integrals. I think integrals is a very daunting name, to be honest. I'm not going to lie. Because derivatives itself were like, okay, that sounds pretty cool, especially to like a non-mathematician. Like derivative is like, oh, this guy's doing calculus. He's cool and everything, But like when you hear integral, I don't know. It just sounds like, because integral, like in English, I guess just means it's an important thing. Like it's an integral part. So like integral, it's very important to calculus. Also interesting fact.
And it has a cool sign.
Yeah, also has a very cool sign. But also interesting fact, and I believe we said this, Isaac Newton, who partially invented calculus, started with integration, which is so weird because nowadays we call the integral the antiderivative. So it's kind of based on the derivative. But the way Newton invented this thing, he invented it starting with integrals. And I think we mentioned it, but I think that's just something to re-mention for sure. That's definitely really commendable.
And the reason why you learn derivatives before integrals is because there's a very nice way to relate the two. And it's, if you have a function that describes the area under a certain curve, taking the derivative of that will give you the actual function itself.
Exactly.
And so there's kind of a flow, right? And differentiation is going forward and integrating is going backwards, right? You have a certain curve, you want to find the area under that curve, or technically the weighted area, because in this case the area can be negative.
And that's true.
You want to take the area under that curve, you would go backwards, integrate that function, and then plug in your bounds, but we're not we're not explaining this very well.
We're not really trying to explain, like technical integration, but again, the main idea is simply while differentiation or the derivative is the rate of change of a variable with respect to another, integration is the same in a little different way. So let me explain this, and I think this kind of explains it. This might explain it well if I do a good job doing this. So if we think of velocity, right? Velocity is the derivative of displacement with respect to time, right? Or the rate of change of displacement or your distance with respect to time, right? As we said, it's just distance over time. Now, acceleration, as I said, is simply your change in velocity over change in time. Now, here where it becomes interesting. We commonly know the acceleration, right, as the velocity. Okay, let's not do acceleration. We commonly know velocity equals distance multiplied by time, right? Like we know that. We equal speed equals distance times time, right? So, now this is where it becomes really cool. If you have, wait, am I thinking about this right? One sec. I think I'm thinking about this a little wrong. One sec. Little brain glitch here. if you have a yeah. Okay, I'm not thinking about this wrong. If you have a curve that represents velocity versus time, and you integrate that curve, you will get your displacement. Right. Yeah, of course. So sorry, I just had a quick brain glitch. I was thinking about the other way, and I'm like, wait, no, that doesn't make any sense. Then I'm like, okay, the velocity times time. So when you have two variables multiplied together, like distance times time, when you're integrating the velocity function, for example, you are getting the distance, you're getting the multiplication. However, when you're differentiating the velocity curve, what do you get? You get acceleration, right? So with the velocity curve, if you take the derivative, you get acceleration. If you take the integral, you're getting the distance or the displacement in this case, right? So the entire idea is how these variables are related, because acceleration is velocity over time. When you differentiate that, you get acceleration. But velocity equals acceleration times time. So when you integrate acceleration, you get velocity.
I think you've repeated yourself like 30 times.
Yeah, I think that made sense. Okay, it made sense in my head. I don't know if it really made sense.
Sure.
But I was basically mainly just trying to explain because these three variables have a very strong relationship that can be explained using calculus, which is distance, velocity, and acceleration. And those are, I think, the most common variables or terms used to explain a lot of terms in calculus. So I was just trying to kind of give a relationship between how they're all related with derivative and integral. I don't know if I did a very good job, but that was my goal to kind of get you that understanding. But yeah.
So when we say area under the curve,
yeah,
right, one can kind of imagine how we would do that, right? So let's say we have like a simple curve that, hits the x-axis, goes above the x-axis, and then hits the x-axis again, right? And then we want to calculate the area that the x-axis and that curve forms, right? It forms some weird shape, and we want to calculate that area. So the simplest way to approximate that area would just be to draw the biggest rectangle that you can inside that shape.
Well, technically outside, right? Because it should incorporate all of it.
Well, no, I'm talking about the inside now. So
okay.
This has to do with what is it called? The infimum, right?
Okay, like the lower and the upper. Okay, you're talking about that.
So you can get a lower bound for your area. So by drawing a single rectangle inside that shape, you're saying, okay, the area is definitely bigger than this rectangle. Yeah. Mm-hmm. And then you can also get an upper bound very easily. Exactly. If you draw a rectangle
outside
around the entire shape and intersecting the x-axis, you know that your entire shape can fit inside that rectangle, and there's a little bit extra, so you can say, well, my able is definitely within this box, which has an easily calculatable area.
Exactly. And I think the easiest example though is just to think of like a regular, like a function that's kind of a square or a rectangle in this case, and that way you can kind of explain that in this case the integral would be very easy to calculate, since it's simply like, I'm just saying that's how you would do it. You would take the area under that curve. So explaining area under just the rectangle, and then moving it on to how you can use this rectangle to then approximate curves. So that's what's, I think, crazy. Yeah.
And so this brings in ideas that we talked about earlier, which about limits, right? And so now let's take a step by step here. If you now give yourself two rectangles, you're allowed to draw two rectangles inside your shape. Let's just say they have equal width. And that way you can get a more accurate representation of what the area is. And now let's say you have 3, 4, 5, and you just increase the amount of rectangles that you're allowed to draw inside your shape. And then, the error, right, the leftover area is going to get smaller and smaller. And then you do the same thing but from the outside, right? The rectangle that engulfs your entire shape, you can limit yourself to 2 rectangles, and then you can adjust the heights, right?
And
to
that's
make it more and more accurate.
And so, sorry, you already mentioned that the lower bound was called the infimum. We should also probably mention that the upper bound is called the supremum.
Well, actually, that's not actually what the
technically
infimum is.
it's the lowest upper bound, yes, but that's basically what it is, right? Like you're calculating the infimum and the supremum, right? When you're doing that.
Yeah, so the supremum is the lowest upper bound, and the infimum is the highest lower bound. Exactly. And so now if we take the limit as, and this is not the formal definition, by the way.
Not at all.
This is just to give you a mental picture. If we take the limit as the amount of rectangles that you're allowed to draw goes to infinity. So you have an infinite amount of rectangles that you can draw, and your area gets very, very accurate, right?
Because because if you visualize it, each rectangle will have a very, very, very small width. So for any very, very, very small change in the function, that rectangle will be able to fully engulf that change, right? Because these widths are so tiny. Because as we're getting infinite rectangles, of course, like the width of each rectangle is nearly approximately 0, right? So it's getting very, very small changes in your function.
And the same thing goes for the rectangles that were above your shape. It gets closer and closer to the actual area of the area under the curve. And so we say a function is integrable when you take this limit as the amount of rectangles that you're allowed to use goes to infinity, and the upper bound and the lower bound equal each other. So basically, as you're approximating from underneath and approximating from above, these two numbers converge to the same value. And then you say, well, okay, this has to be the exact value for the area under the curve.
And I think that's also where limits play a pretty important role. Like, because everyone thinks it's only used for derivatives, or limits are only used for approximating these functions, but it can also be used for so many other things. Just like as something approaches something, what happens to something? Like it's very, very general, because I know many people think, especially for example, me in high school, I used to only think of limits when it came to f of x or something like that, like some kind of function, mathematical function. But in this case, we're just taking rectangles. Right, we're just taking rectangles, and we're taking as the number of rectangles go to infinity. So it's not even that mathematical. It's very, very general. And I think that's also where we can see that limits play such an important role, because as we take this limit as the number of rectangles go to infinity, as Parker just stated, we simply get both of these values converging to the same number, which is the integral. Yeah.
Exactly. And what I just described was actually called Riemann Integration, which is the act of taking these rectangles and taking the amount as it goes to infinity, and then you get a certain value. And, Riemann Integration is very good to build up an intuition for what integration actually is, but it is not the most effective way to directly calculate areas under the curve. And the easiest way is to take an antiderivative, which easily enough, it's not actually in some cases it's not very easy, but you just have to pretend like you're given the derivative, and you're trying to find from that derivative, you're trying to find the original function.
Exactly.
What you'll see is that there's not just one function that you can find. There's actually a family of functions. And those families of functions are simply differentiated, no pun intended, by a constant, right? Because as you can probably imagine, if you have a constant function, so f of x is equal to 1 everywhere, what is the rate of change of your function? The rate of change of your function is just 0, because everywhere you go it's 1. Your function is not changing at all.
Exactly.
And so if you're given a rate of change, let's say your rate of change is some function, you find by taking the antiderivative, you find the original function. But what tells you that your original function is not that function, but plus 1? That would have no effect on the rate of change of your function, because actually this would kind of take some understanding
Yeah,
of how
that's, I
you
was
take
just going to say,
derivatives.
this kind of takes a little bit of an understanding of how
Yeah.
differentiation relates to constants and stuff like that. So, I mean, basically, differentiation does
Yeah.
not, or constants don't affect the derivative. So if it's like, if your function is, for example, x plus 5, or x plus 10, or x plus 5 million, the derivative will be the exact same. But your integral will be different. Because
Yeah,
again, it's
absolutely.
the opposite of the derivative, right? Because if it doesn't matter for the derivative, it matters for the integral. So it's kind of like that. Also, a quick note, when you were talking about Riemann integration, also like a common term that people use is Riemann sums, because basically the integral sign is mainly used when you're taking the summation, you know, that big sigma that some of you might have seen. So like when you're taking the summation of the areas of all of these rectangles, and as the rectangles go to infinity, you get your integral. So like your Riemann sum, if I'm not mistaken, I believe the Riemann sum is like the Riemann sum to infinity is the integral, right? So I think that's
Yeah.
how a lot of people define it. So yeah, so like Riemann integration is basically, it's the same idea, but it's just the sum is kind of like the formal way to introduce what the integral actually is in a way.
Yeah.
In a way.
And you always need to make sure that your function is actually integrable.
Always, yeah.
One thing I'd like to say to all of our like listeners out there is,
Okay.
you know, if you're in university in mathematics, you've probably dealt with this type of function before. But imagine a function that is equal to 0 for every rational number, right? So every number that can be described as a fraction, it's 0. And then every number that you can describe, or that you can't describe as a function, so every irrational number, it's equal to 1. And now I want you to think about, is that integrable? Can you take the area under that function from, you know, any point to any point?
We
right?
can do a
So that's an interesting idea to also think about.
Okay.
And also, when you're taking the area under a curve, you are taking it from one point to another, right? So you have, right, what are they called? Initial, final
like
conditions?
technically it's lower and upper bounds. They're bounds.
Sure.
They're bounds
Sure.
technically.
So you have a lower and
because
upper
you're
bound.
bounding your area that you want to integrate, right? So they're called lower and upper bounds.
Yeah, so if this is mostly a question or a thought for people who have never done integration before, because the answer is pretty obvious, to me at least. Probably not to some people, but let's say you are integrating. You want to find the area under a curve from A to A, from one point to the same exact point. Is there an actual value for that area? Maybe, maybe not. I don't know. Have a think about it.
No,
I
I
can't
was
hear
just
you.
Say?
I couldn't hear you for
No.
a second.
I was just kind of giving like a sound effect, like what, like, you know, that's crazy, kind of thing. Like I was just
Okay.
trying to, no, because you were saying some things like, you know, like, oh, you guys can think about this, and I
No,
was just, you
yeah.
know, chilling. So I'm like, what? Can you do that?
No, I just couldn't hear you, but
Oh,
I
okay,
can hear you
okay,
now. So
yeah. So
pretty
I
much
think,
talked about a lot of stuff
yeah.
here.
I mean, I think okay. Quick summary. Talked about limits. Talked about why limits are so important. Why calculus is so important. Spoke a little bit about derivatives, higher order derivatives. You know, velocity, acceleration, all that good stuff. And finally ended it with some integration. I think we got some good progress. So for any high school student out there who's listening to the Math and Physics podcast, know that integration is going to be a lot of fun. You don't do it in high school, right? Unless you're taking like an AP or an IB course. Because I believe, 12 AP and all that stuff has it. So, yeah, that's been episode number 40.
Absolutely. One thing that I want to say before we end it, just a little sneak peek for everybody that's in high school. Whatever you learn in high school calculus, university, you're just basically going to be relearning everything you just learned in your first year.
Very
And
true,
then in
very
your
true.
second year, you're just going to be relearning everything you learned in your first year, but just expanded to various dimensions.
To be honest, though, I think it's really nice that we relearn everything in the first year of university because it's definitely taught in a much, much, much more understanding way. So
Understandable.
Definitely recommend university.
If you want to learn math, go to university.
Yeah, for sure.
It's recommended.
It's useful.
Alrighty. If you're listening to this podcast right now on Spotify or Apple or iHeartRadio, make sure to follow, or anywhere else you might be listening to this podcast. Make sure to subscribe, follow, leave a comment. We will answer your comments, definitely. And also send us an email.
Yeah.
If you want to follow us on Instagram, it is at math.physics.podcast. If you want to send us an email, just add at gmail.com at the end of our Instagram handle. If you want to follow us on Twitter,
true.
Physics Pod.
Pod, yes.
That's it. Our name is actually too long to do a
I
Twitter
think
handle.
it's kind of sad. Yeah.
If you want to leave a like on the YouTube video, subscribe for the YouTube
Subscribe on YouTube, man.
channel.
Yeah, for sure.
Come watch us on YouTube.
Our YouTube channel deserves needs some more recognition right now. So if you guys are on Spotify, definitely go check out our YouTube because we're starting to every episode, as already mentioned, is now going to be on Zoom. So I mean, I think that's really cool. And obviously, the only reason we're doing it on Zoom is so that people on YouTube can watch it because I guess we can't really post the video anywhere else. Mm-hmm. So go ahead and watch it, like it, subscribe, and comment. We're always replying to comments. Episode 40.
So yeah, this has been the 40th episode of the Math and Physics podcast. Thank you so much for listening. Make sure to tell a friend today.
Make sure to tell a friend
that might enjoy our content. Tell
Absolutely.
a friend. Tell them to come on over and listen to an interesting episode of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. And we'll see you soon.
See ya.